Welcome to AlphaStar Video, an overview of MCQ Chopped and its modules. MCQ Chopped is a software toolset designed to characterize chopped fiber reinforced composite material properties based on effective particles and matrix material properties, assuming uniform orientation through the width and length of a represented volume element while including the effect of material nonlinearity and manufacturing geometric and material defects. Using a de-homogenized multi-scale material modeling approach, MCQ Chopped delivers accurate predictions of strength, stiffness, damage, and failure in response to service or complex loads. Here we are in MCQ Chopped. Please note the basic construction of the GUI. At the top, we have the main menu, followed below by the toolbar. On the left, the tree structure that supports libraries and projects. To the right, the panel view for tutorial instructions and visualization of analysis results. Finally, on the bottom right, the status display, providing system feedback. Now that we have summarized the capabilities of MCQ Chopped, let's identify a tutorial with a complete solution and open a project related to that tutorial to observe the calibrated materials and the analysis results of various modules associated with MCQ Chopped. Please note that the fully loaded tutorial contains the calibrated material model, results of analysis, and step-by-step instructions in the panel view explaining how an end user can achieve those same outcomes. This information includes the breakdown of the problem in sections, a description of the objectives, requirements, and expected outcomes, an introduction, specification of the available analysis modules, summary of the material library, review of material input including available test data and critical assumptions, and finally, the full set of instructions. As with the other MCQ products, MCQ Chopped delivers a de-homogenized, fully calibrated material model that includes ply orientation through the thickness and the effect of defects to provide an accurate prediction of strength. Now let's explore the material inputs. Please recall MCQ generally reverse engineers the in situ constituent properties for the fiber and matrix from test and virtually reconstitutes the composite to continue the analysis. However, in the case of chopped particles, the end user must also account for the characteristics of the particle, i.e. the shape, fiber, ellipsoid, disc, sphere, or chopped tape, the type, straight or wavy, as well as size, weight ratio, volume ratio, and void volume ratio. Further, the end user can address uniform or non-uniform dispersion, as well as details of the interface. The road to calibration and identification of a complete failure envelope for our chopped fiber composite involves the step-by-step application of MCQ Chopped modules to properly characterize, qualify, validate, and ultimately extrapolate behavior. Recall chopped mechanics takes vendor material properties, including defects, to estimate material properties with respect to the aligned layer or other configuration. In our current example, note the list of material properties as well as various potential alignment configurations. For our aligned layer, we have volume fraction for matrix, void, and particle, modulus per direction, Poisson's ratio in plane and out of plane, strength, density, and other variables. As would be expected, this data supplements our other modules. Now let's examine the results of orientation distribution determination, in which we take the flow and cross-flow modulus to define orientation distribution through the thickness with A11, A22, and A33. As can be seen by the results, we can simultaneously observe orientation distribution with regard to all three directions, or examine orientation distribution with regard to a specific direction on a case-by-case basis. We will now move on to chopped characterization, which allows the end user to visualize the relationship between a line layer and other configurations, constituent material properties, and manufacturing variables, particularly those unique to the chopped fiber or particle. In this particular example, the focus will be on the variation of a material property as a function of chopped fiber length. Using the drop-down menu, we can visualize a line layer modulus in the 1-1 direction versus length, a line layer modulus in the 2-2 direction versus length, a line layer modulus in the 3-3 direction versus length, a line layer in plane shear modulus versus length, and both a line layer out of planes shear moduli versus length, as well as other material properties that can be compared to length. Now let's examine the output of the material nonlinearity module. If you recall, the module takes the matrix stress-strain curve and develops a stress-strain curve for a unique configuration such as the aligned layer. Accordingly, let's first take a look at the in-plane stress-strain curve for the matrix, and now examine the output of the module in terms of a stress-strain curve for the chopped composite in the 1-1 direction, a stress-strain curve for the chopped composite in the 2-2 direction, and similarly a stress-strain curve in the 3-3 direction. In the case of the aligned layer nonlinearity, let us first observe the original stress-strain curve from test, and then compare the stress-strain curve of the reconstituted specimen to the stress-strain curve of the test data. There appears to be good agreement between the two curves. Continuing the analysis, we can now observe the optimized calibrated stress-strain curve, which will provide the foundation for our upcoming higher-level analysis results. With regard to the progressive failure module, we are immediately presented with the results of the through-the-thickness damage for various ply layers at given load steps. Here, initial damage occurs in response to longitudinal tension and is later supplemented by in-plane shear. Once damage initiates, it always incorporates modified distortion energy or twisting and rotating leading to delamination. Similar observations can be made for ply stress in terms of a given direction, a given layer, and at a particular load step, which provides a mechanism to determine when and where damage initiates. Finally, the PFA ply stress provides a convenient screen to simultaneously display directional ply stress, sigma XX, sigma YY, etc., for every ply at a given load step, which provides a clear visualization for a demonstration of increasing stress and potential triggers for damage. Finally, please recall that the design failure envelope module predicts damage initiation and final failure of coupons subjected to biaxial loading. The image reflecting the biaxial stress state clearly identifies stretch states in which damage does not occur, damage initiates, and accumulated damage leads to fracture or failure. The tool provides a mechanism to concurrently present test data in order to better assess the efficacy of the prediction. In addition, by selecting shear strain, it is possible to observe the design failure envelope in terms of a biaxial strain state. Both sets of data can provide a designer with critical information to properly address service loads and meet specification. This concludes our MCQ Chopped video. If you have any questions regarding the content or simply seek a more in-depth conversation, please contact AlphaStar via email at info@alphastarcorp.com or visit us on the web at www.alphastarcorp.com.